We're going to be reviewing the experiment that was performed on Traversable Wormhole Teleportation Protocol. And this is looking at a very important idea within unified physics and quantum gravity, that is ER equals EPR. Einstein-Rosen bridges equals Einstein-Podolsky-Rosen correlations. And I'll discuss a little bit more what that means exactly. But this is essentially an experiment that was performed that is testing quantum gravity in the lab. And so, within science, this is critically important that if there's a theory, an idea, the way that we assess the veracity of that idea is to test it out, run an experiment and see if it holds up and has validity. Sure enough, in this experiment, researchers have purported to verify the veracity of this postulate, ER equals EPR, and have claimed to have demonstrated that they can perform quantum teleportation using a traversable wormhole. So we have this article available on the Resonance Science Foundation. If you go to the science section, I'm going to post the URL, the hyperlink to this article in the chat. That'll be made available as well when this video is posted, so that there will be easy access to the full article. It was written by myself, physicist Dr. Inez Ordaneta, and Nassim Herman. So the main thing we're looking at is holography, the holographic principle, holographic physics, and the correspondence with space-time geometry, gravitational interactions, or wormholes. Wormholes are direct links between two disparate regions of space-time in a highly curved geometry. They may seem like the stuff of science fiction. However, studying these predicted multiply connected geometries of space-time could be the key to making concrete the tantalizing link between information and matter that has confused conventional physicists for quite some time now. This link between information and matter that is provided via the study of wormholes is something that we explored in great detail in one of our publications, the Unified Space Memory Network, From Cosmogenesis to Consciousness. And one of the main postulates within this publication, this paper of ours, is the role of the micro wormhole network of space-time, multiply connected geometry of space-time at the Planck scale, and how this is central to so many properties of the universe, particularly informational properties, and that this micro wormhole network is underlying things as diverse as the organization and ordering of matter in general in the universe, and the biological system in particular, and how it is involved in the information processes associated with intelligence and sentience in the universe as a whole. And in specific examples are consciousness as well. And if you look at the publication, you can see this described in some detail. So like, here's just an example where we're depicting the role of multiply connected space-time geometry in organizing matter. And the negentropic effect of a multiply connected geometry on ordering physical systems in the universe as an organizational parameter, impetus even. So if you start off with a very simple configuration of mass energy, this Planck electron plasma, you can think of this as kind of the early stages of the universe, before anything has formed, before galaxies have formed, before stars have formed, these kind of things. If you were to follow kind of random interactions, the most likely outcome of this pathway would be to end with an electron proton plasma. The least likely outcome under random interactions, and this as well includes random values for the constants and the physical forces mediating interactions between mass energy, between particles. The least likely outcome is to end with anything with significant complexity. However, we describe how the information transfer and the entanglement that is generated via the micro wormhole network, the multiply connected geometry of space-time at the Planck scale, actually generates a negentropic force that drives matter into ever greater complexification and synergistic organization, leading to such complex systems as life, as the biological system, as the living system. So this idea of entanglement being equivalent to traversable wormholes, and the link between wormholes and information and matter in the universe is very important to the physics that we're working on here. It's very important to unified physics in general. So the experiment is based on looking at this postulate called the ADS-CFT holographic correspondence conjecture. And we're going to discuss exactly what that is and what that means in more detail as we proceed. But it's based on this report published in Nature, Traversable Wormhole Dynamics on a Quantum Processor. So researchers utilize the high fidelity entanglement of a quantum computer to test a theory of quantum gravity, to see if they could perform quantum operations, operations with these entangled bits, these qubits, to see if the signature of those operations match the description of a gravitational interaction, match the signature of a wormhole. And they purport to have demonstrated that it does. So this is the Google Sycamore quantum computer. By studying the quantum theory on the processor, researchers claim to have been able to leverage the ADS-CFT correspondence to probe the dynamics of a quantum system equivalent to a wormhole in a model of gravity. And so the ADS-CFT correspondence is the preeminent model of the holographic principle, the preeminent application of the holographic principle in physics. So it's somewhat surprising that a quantum computer is an ideal platform to investigate this connection between information and matter. And the trick is to use that correspondence called ADS-CFT, which establishes an equivalence between a theory that describes gravity and space-time, the anti-de Sitter space-time, and wormholes, with a quantum theory that does not contain gravity at all, a CFT conformal field theory. So translated from the language of quantum information to space-time physics via the holographic principle, the experiment let a particle fall into one side of a wormhole and observed it emerging on the other side. This is part of a larger idea within physics on attempts to achieve unified physics, that is, unification of quantum field theory, quantum mechanics, with general relativity. Quantum mechanics describes the behavior of particles, the behavior of matter, mass energy at the atomic scale. And general relativity primarily describes the gravitational force, gravitational interaction, which, because it appears so much weaker than the other fundamental forces, it involves a large number of particles. So that's much beyond the atomic scale, typically, in most circumstances. The holographic principle appears to be one of the most possible ways to unify these two disparate fields of physics. It comes from the actual technological application of holography, in which a three-dimensional object using coherent laser light and wave interference, the information of that three-dimensional object can be completely and totally encoded on a flat surface. And this is sometimes thought of as, okay, if you have a three-dimensional object and it's being encoded on a two-dimensional surface. In reality, nothing is two-dimensional, because even what appears to be very flat to us actually has volume. So it's still 3D. But it is very interesting that a flat surface can encode seemingly all the information of a 3D object via holography. Within our work, we take this idea of holofractogramic physics, and we, as we are investigating nature, investigating some of the properties of the universe, we see that it has, in many instances, cases that are best described via similar properties as a hologram. For instance, the role of wave dynamics in the field theory, hollow information, that is a property of holograms in which the subunit, every subunit of the hologram contains information of the whole. So if you have a holographic plate with they can project out a 3D image. If you half that plate, break it into two, each one of those halves will still contain the whole image. And you can continue dividing it, and each fraction of that plate will still contain the whole image, albeit at lower resolution. That is because each subunit of that information contains the entire set of information of the 3D encoding. This also has to do with the observation that many systems in nature that display properties of fractality. You can see the properties of fractals displayed in many instances. And that has to do with like properties like scale invariant complexity, self-repeating patterns, and feedback feed-forward dynamics. Scale invariant complexity is a really important one, which is that no matter how much you change in magnitude of scale, so if you zoom down and to smaller and smaller scales, or if you zoom out, up or out to larger and larger scales, the level of complexity doesn't vary, doesn't change. Scale invariant complexity. Now, if our universe has those kind of properties, which we observe it does, that has very significant implications, because let's take the mesoscale, the biological system, the living system. At the mesoscale, we have the complex neuronal network of the brain. It can be demarcated by a certain level of complexity. Well, if it's part of a fractal system, and you have scale invariant complexity, you can expect to see that same level of complexity reiterated at different scales, at smaller scales in the universe and at larger scales. And indeed you do. For instance, in the cosmic web, it has been mathematically demonstrated via power law analysis that the cosmic web has some of the same levels of complexity and information processing capacity as the human brain. That's at the largest scale of the universe. You go to the smallest scale, the Planck scale, where you have the multiply connected geometry, the micro wormhole network at the Planck scale. Again, it has the same level of complexity and the same information processing capacity as the human brain. Well, the human brain is what material scientists and those in the neurocomputational paradigm posit produces consciousness. Well, if you have the same level of complexity at the larger scales and the smaller scales, what does that say about consciousness in the universe? Our application of the idea of holography is much more general in fractogramic physics than in the conventional application of holographic properties within physics, unified physics, which is the idea of the holographic principle, which is much more specific on what it's discussing, what it's describing as holographic. It doesn't include a lot of these other properties that we've identified that apply to the universe and that are very important. But this idea of the holographic principle in physics comes from work on thermodynamics and looking at the information capacity of a volume of space. And this is work initially taken on by Bekenstein, and later developed by Gerard de Hooft. But just to disambiguate holofractogramic physics from the holographic principle in conventional physics, according to the Bekenstein bound, the entropy of a black hole is proportional to the number of Planck areas that it would take to cover the black hole's event horizon. And this leads to very interesting conclusions, albeit somewhat erroneous conclusions, that the maximum entropy of a volume is restricted to the surface area of that volume. And this is the birth of the holographic principle because it seems that the two-dimensional, quote, two-dimensional, unquote, surface area is determining the information content of the volume. So, that's a kind of holographic principle there where your 3D volume is fully, all the information is encoded in this 2D surface area. And so this principle was suggested by Gerard de Hooft in 1993 and then developed by Leonard Susskind. And he plays a very prominent role in all of this. His name will be coming up again as we look at the experiment that was done. And it just points out that the information contained in a volume can be represented by information over its bounding surface. So when physicists such as Jacob Bekenstein and Stephen Hawking tried to compute the information content of a black hole, they found to their surprise that it's given by the area of the event horizon, not by the volume of the black hole. So it looks as if the information inside the black hole was written on the event horizon. The holographic principle is related to the generalized second law of thermodynamics proposed by Bekenstein, stating that the sum of black hole entropies and the ordinary entropy outside the black hole cannot decrease. And this led to additional developments in physics, such as the information loss paradox that arises within black holes. Now, it should be noted that this idea that the maximum entropy is restricted by the surface of a volume of space and not by the volume has been shown to be somewhat erroneous. It's not entirely correct. And particularly a work by Busso demonstrated how this idea falls short in many instances. The study of black hole thermodynamics and the information paradox led to the idea of the holographic principle. The entropy of matter and radiation in a spatial region cannot exceed the Bekenstein-Hawking entropy of the boundary of the region, which is proportional to the boundary area. However, this space-like entropy bound fails in cosmology. It does not hold true in our universe. So that's a major problem for any theory, is if it doesn't actually comport with the reality of what we observe. Now, Busso was able to show how, in many instances, the entropy is contained in equivalent to the volume of a region of space. However, in his application, he still preserved the holographic principle. And it has been updated, advanced to now it's called the Busso bound, Busso's holographic bound. And so this is just kind of important to point out that, that original Bekenstein bound has been shown to be erroneous. So, the information content of volume is not absolutely restricted to the surface horizon. This leads us to the holographic duality in physics, which is one of the leading theories for a unification of physics, quantum mechanics, and general relativity, a principle for quantum gravity. And it has to do with the ADS-CFT correspondence conjecture, anti-de Sitter conformal field theory correspondence. So much like a 3D hologram emerges from the information encoded on a 2D surface, a 5-dimensional space describing gravity, that is anti-de Sitter space, the bulk interior region, is being holographically projected from the lower dimensional quantum field theory, the quantum info boundary, which the mathematics that describe this boundary do not include the gravitational force. There's no gravitational interaction in the description of the quantum field theory. But what this correspondence conjecture, this holographic duality, has shown is that the gravitational interaction in this bulk anti-de Sitter space can be shown to be absolutely mathematically equivalent to a quantum description of the information on a lower dimensional boundary, a lower dimensional surface. In other words, the seemingly different theories, ADS and CFT, could both describe the same physical system, showing that the theories are, in a sense, equivalent, even though they each include different numbers of dimensions, and one factors in gravity, while the other does not. So the discovery that the maximum amount of information that could fit in a region was proportional not to its volume, but to the surface area of the region's boundary hinted at an intriguing relationship between quantum information and the 3-dimensional spatial world of our everyday experience. This relationship has been epitomized in the kind of somewhat joking phrase, "it from qubit," which is an update of John Archibald Wheeler's "it from bit" statement, describing how matter, that is it, emerges from quantum information, or qubit. The ADS CFT correspondence allows physicists to connect objects in space, like this person here. These are space-time frames. So as time goes on, these are the evolution of the spatial dimension. The correspondence allows physicists to connect objects in space with specific ensembles of interacting qubits on the surface. That is, each region of the boundary encodes in quantum information the content of a region in space-time, such that matter at any given location can be constructed from the quantum information. This allows quantum processors to work directly with qubits while providing insights into space-time physics. By carefully defining the parameters of the quantum computer to emulate a given model, physicists can look at black holes, or even go further and look at two black holes connected to each other, a configuration known as a wormhole, or an Einstein-Rosen bridge. So it's because of correspondences like these, the ADS-CFT correspondence, that holographic theory is seen by many as a bridge between the seemingly disparate physics frameworks of general relativity that describes a very large scale where gravity is the governing force, and quantum mechanics that does not normally incorporate gravitational or space-time geometry interactions at all. And so, it's a very compelling idea that the idea being that our 4D space-time is encoded informationally in a lower dimensional space. So our 4D space-time is encoded in 3D space, in voxels, and quantum entangled voxels, if voxels are bits, qubits. So our 4D, our space-time, is somewhat illusionary as a projection from a pure spatial information. That's what we call space memory. The idea that the space-time is emerging from information encoded in space at the Planck scale. And so, indeed, the generalized application of the holographic principle has been used to compute and output precise values for the physical constants, physical forces, even the values of the mass and radius of fundamental particles. So that generalized holographic solution that describes quantum forces like the strong force arising by gravitational interaction was published by Nassim in his 2012 paper, Quantum Gravity and the Holographic Mass. Now, in an abundance of caution, I'm going to make sure that we're clear on the idea of the holographic principle, because in many popular articles and popular discussions, it's presented completely wrong. It's presented as if 3D space is somehow encoded on a mysterious two-dimensional surface, a literal 2D surface. And this is often how the holographic principle is presented. But this is an erroneous depiction. It leads people to a wrong picture of what is actually being discussed and described. Because, as I mentioned, we live in a 4D spacetime. So if we're talking about a holographic principle for our universe, the 4D spacetime is encoded in a lower dimensional 3D space, what we call space memory. So when you see depictions like this, just keep in mind that the person is not entirely clear on what is being discussed with the holographic principle. And it stems from the fact that oftentimes toy models are used. And so to simplify the mathematics, to simplify the physics, the holographic physics will be worked out in a toy model that might only have a three-dimensional space and the information is encoded on an actual 2D surface. You can do that with mathematics, but our real world doesn't have 2D surfaces. So if anything, the information is encoded in 3D, not as Planck pixels, but as voxels, volumetric pixels, as Nassim Haramein has shown with the Planck scale voxelation that generates the holographic mass. This is one reason why Haramein's generalized holographic solution was revolutionary. He showed that the holographic relationship has to do not with information encoded on the surface horizon, restricting the amount of information in the volume, the normal kind of idea of the Bekenstein bound, but that the volume entropy is shared holographically via micro wormholes with all particles in the universe. And the observed mass only arises because of the restriction in total volume entropy information that can be expressed on the surface horizon through the micro wormhole network. So Nassim's generalized holographic solution very much involves that multiply connected space-time geometry, that wormhole network, because you have a much larger volume entropy information inside your fundamental particle, inside your black hole, then can be expressed on the surface. And it's actually the restriction that makes this black hole appear to have a much smaller mass than its actual holographic mass. And as well, this multiply connected geometry is one of the reasons for some of the holographic properties of our universe, because any one black hole is sharing information with all other black holes in the universe via this entanglement network. And if we're talking about microscopic fundamental black holes, protons, the information of any one proton is shared with all other protons in the universe, which is why the holographic mass of a proton equals the mass of all protons in the universe. And this as well explains quantum mechanical properties like entanglement. The protons, indeed all black holes, are connected via space-time geometry, Einstein-Rosen bridges, wormholes. And that's how you get properties like Einstein-Podolsky-Rosen correlations or quantum entanglement. Just real briefly on the idea of ER equals EPR. It's kind of an interesting situation where Einstein, who was not completely satisfied with the way that quantum mechanics was developing, in association with Podolsky and Rosen, he came up with a Gedanken experiment, a thought experiment, in which they showed how the modern interpretation of quantum mechanics and the predictions of quantum mechanics showed that it must be an incomplete theory, because it was showing non-local interactions. What interactions between particles, it predicted interactions between particles that seem to occur faster than the speed of light. And that's a big violation of general relativity, because general relativity and special relativity are founded on the principle that nothing travels faster than the speed of light. That's how you get the relativity of simultaneity that is the underpinning, is the foundation of the theory of relativity. Now, again, in many popular articles discussing this latest experiment and discovery of a traversable wormhole being equivalent to quantum teleportation, many the authors and commentators have said that Einstein hated quantum mechanics, but this is just totally wrong. Einstein didn't hate quantum mechanics. He founded quantum mechanics. With his work with the photoelectric effect, he described the photon. I mean, he is one of the founders of quantum mechanics. He didn't hate it. He just saw it as an incomplete theory. And in many cases, it is. And he attempted to demonstrate this with the EPR paradox. Now, the thing is that that non-local interaction of particles, since they Einstein, Podolsky, and Rosen published that paper, has been empirically observed. And we build devices based on it. They're called quantum computers. Entanglement is a very real phenomenon. And it perhaps wasn't the best example to choose to try to show how quantum mechanics is an incomplete theory, which it is. But the interesting thing is that Einstein, at the same time that he proposed this paradox, the Einstein-Podolsky-Rosen paradox, he produced the solution to it. Again, with one of the other authors of the original paper, Rosen, Nathaniel Rosen. So Einstein and Rosen published a paper to try to solve the problem of point particles, the particle problem in fundamental physics. That the electron is described as a point particle, a singularity. And this leads to all kinds of severe problems, like an infinite bare mass for the electron, an infinite charge, bare charge for the electron. the point-like description of that of the electron as a particle leads to all kinds of outputs of infinities. And it's just very clear that the electron is not a point-like particle. But one of the ways that Einstein and Rosen solved this is by extending that point-like description, extending the geometry, the space-time geometry of it, out as a bridge-like structure, an Einstein-Rosen bridge. And they solved the particle problem of the electron via the space-time geometry of a wormhole. Now, we're at a point now where we can look back at these two Gedanken experiments and these two papers, and we can see that, or if particles are wormholes, and that allows for non-local signaling within relativity, interaction, faster than light interaction across any distance, any time, any separation in time. And we have that observed behavior in quantum entanglement, then maybe ER equals EPR, or Einstein-Rosen bridges equals Einstein-Podolsky-Rosen correlations. So quantum entanglement, the physical mechanism of quantum entanglement, is actual wormholes in spacetime, actual geometry of spacetime. This is equivalently described via a gravitational interaction in the holographic dual interpretation of what is occurring. So this quantum entanglement is no longer some mysterious ethereal process. It is a physical connection between the two particles in spacetime via the underlying geometry. So it's kind of exciting because at this time, this idea is testable with quantum computers. So we can run these ideas of quantum gravity in the lab. By studying this quantum theory on the quantum processor of the quantum computer, researchers are able to leverage the ADS-CFT correspondence to probe the dynamics of a quantum system equivalent to a wormhole in a model of gravity. So while the ER equals EPR postulate has been an intriguing idea, any idea in science must have observational and experimental backing to pass into serious consideration. And especially when you're talking about wormholes, because for many, and especially scientists and physicists, the idea of a wormhole is just too much in the realm of science fiction. So you're going to absolutely need observational and empirical data to show that this is not an idea taken from science fiction. Science fiction has ran with this idea that is a foundational idea within physics, the Einstein-Rosen bridge, the wormhole. So now there's a potential step forward in this effort with tangible observational evidence of EPR equals EPR, an experiment that utilized qubit teleportation with the quantum computer. In the simulation performed in the quantum computer, the analog of the particle to be transferred through the holographic wormhole is a quantum bit or a qubit. Alice's qubit is sent to Bob's qubit via quantum teleportation, and that is equivalent to passing through a traversable micro wormhole. When the particle passes through the wormhole, it is undergoing quantum teleportation, a process by which its information can be sent between two distant quantum entangled initial and final states, representing the black holes at both extremes. Authors examined the process of information transfer through the holographic dual traversable wormhole, and the experiment proved satisfactory as the qubit was successfully recuperated at the other side of the wormhole. And importantly, they showed that this is best described, the quantum teleportation is best described as occurring through a traversable micro wormhole. Traversable wormholes were recently shown to be possible by Daniel Jefferies and Ping Gao, as well as Aaron Wall, sorry. Naively, in some of the first computations in mathematics around wormholes, it was shown that they very quickly, almost instantly, in fact, collapse because there's gravitational interaction along that bridge-like structure, the so-called throat. And so it pinches off, it collapses very rapidly. And so for a long time, this gave many skeptical physicists free rein to say that wormholes are impossible and are in fact just science fiction because the mathematics show that they close off immediately. But those are simple constructions. They're using static black holes, so static solutions. So they're not factoring in spin. They're not factoring in electric charge or magnetic field effects of the black hole. And so under the very simple static solutions in which nothing's moving, so no dynamics, under the static solutions, the wormhole closes off. But there has been many computations recently and papers published recently that show that when you apply a more realistic case scenario and have a dynamic black hole, one that is spinning, one that has electric charge and magnetic field interactions, that the wormhole is in fact stabilized. It does not instantly collapse. And so all black holes are wormholes, and all black holes are connected via wormholes. Now, Daniel Jefferies and Ping Gao and Aaron Wall showed another way in which wormholes are stabilized and maintained, and it's a very interesting effect where when black holes are quantum entangled, when there's a quantum connection between them, there's a gravitational back reaction that stabilizes the wormhole, making it a traversable wormhole between these entangled black holes. They become mouths of a wormhole. So it's a very interesting situation where the entanglement itself is helping to stabilize the wormhole. And that's a very exciting development. Now, one of the important things about their particular mathematical computation of this is that it's traversable as long as negative energy is being sent through the wormhole. If you send positive energy through it, this quantum connection and the gravitational back reaction is cut off and you'll get a collapse of the wormhole. Now, I'm not entirely convinced about that kind of solution because, they're only looking at stabilization of the wormhole with that quantum connection. They're not taking into account the role of spin and charge and the Casimir effect on keeping the wormhole stabilized. But nevertheless, it's an important consideration for the experiment that was done because they can simulate putting positive energy or negative energy through the traversable wormhole. They can simulate that on the quantum computer. And this is what they did, essentially. So they showed that the positive or negative energy, it's like a shock wave, a deformation of space-time that propagates at the speed of light. It can either keep the wormhole open or close it. So the presence of negative energy in a traversable wormhole is similar to negative energy in the Casimir effect, where vacuum energy pushes together closely spaced plates. In both cases, quantum mechanics permits the energy density at a given location in space to be either positive or negative. On the other hand, if the wormhole experienced a shockwave of positive energy, no information would be allowed to pass through. And so they could simulate this with the quantum computer. And when they did this, they were able to show that there was an asymmetry in the results. They favored the simulation of negative energy and negative energy shockwave passing through the traversable wormhole. Now, just a little bit on the technicals of what was done. Jeffries and Gao had shown that the quantum teleportation could be shown to be equivalent to information passing through a traversable wormhole. Now, the pencil and paper solutions given by theoretical physicists show that you would need an arbitrarily large number of qubits to actually test this. You'd need many more qubits than what are actually available on today's quantum computers. So to actually test this, the number of qubits needed to be reduced. One of the problems with that is that as you reduce the number of qubits, the fidelity of that quantum system to be equivalent to a gravitational interaction is reduced. So as you reduce the number of qubits, it becomes less and less like a gravity signature. But they were able to have this pretty clever application where they used a neural network and machine learning to actually simulate this large number of qubits with a small number of qubits. And they were able to maintain that same signature, that same gravity dynamics, and a smaller number of qubits. It was a pretty clever application that they did using neural networks and machine learning. Now, this SYK model, this is Sachev-Yekitiev model. It exhibits an explicit holographic duality, meaning that it has quantum dynamics that look like quantum gravity effects in an emergent space. It's intrinsic to the quantum system. Intrinsically, it has a gravitational holographic duality. The quantum dynamics look like quantum gravity effects. So because of this, it's possible to do quantum gravity experiments on quantum processors utilizing what are called SYK model of qubits. And some of the more recent work, particularly by Susskind, have been heavily leveraging the SYK model to actually advance even the EPR-CFT correspondence conjecture. And if I remember, I'll discuss that point in a little bit more detail at the end here. So to create the wormhole, researchers started with a large quantum system and treated it like a neural network. Back propagation through the neural network updated the parameters of the system in order to maintain those gravitational properties while the number of qubits was reduced. The training data set compared dynamics of a particle traversing a wormhole propped open with negative energy and collapsed with positive energy. By ensuring the learned system preserved this asymmetry, they obtained a sparse model consistent with wormhole dynamics. So additionally, they were able to simulate positive or negative energy shock waves passing through this traversable wormhole, so they could test if the quantum teleportation was more efficient with a negative energy shock wave or a positive energy shock wave. So here is the experiment in actuality. They've got the quantum computer. They've got 7 qubits that are quantum entangled. They used an 8th qubit is swapped in, and that entanglement state propagates through the entangled 7 qubits on the left here. Let's call these Alice's qubit state. And so keep in mind all along that this is equivalent to they've injected a particle or they've injected information into one mouth of a wormhole. Now they use a magnetic pulse to rotate the qubit states. And they can tailor this magnetic pulse to be equivalent to sending a negative energy shock wave through the wormhole or a positive energy shock wave through the wormhole. So they're simulating that negative energy or positive energy geometry of space-time, because it's a deformation propagating in the space-time geometry, either negatively curved or positively curved. If it's a positively curved deformation, it causes the wormhole to collapse and it's no longer traversable. If it's a negative energy deformation of space-time, it goes through. Now that when they did that, the information is quantum teleported to Bob's qubit system. And these entangled qubits now have essentially cloned the qubit state over here, that they've fully recreated the qubit state. It's as if it was teleported from one system to the other. And what the researchers showed is that it's as if that teleportation physically occurred via a wormhole connection. Because they're able to simulate whether it's a positive energy or a negative energy pulse with that magnetic pulse, that they're able to test it many times and see whether there is a difference between the negative energy pulse and the positive energy pulse. And they observed a slight asymmetry between the two energies, showing the key signature of a traversable wormhole. So it becomes a fairly significant result, and it's very suggestive that indeed they were demonstrating the equivalence of this quantum teleportation with traversing through a wormhole. So for those who are perhaps a little bit more technically minded, this is a schematic, a diagram of the circuit that was actually used, and the actual teleportation protocol. So there is additional information for those who want more of the technical steps of the protocol. I don't think we'll go into this in too much detail here, mostly in the interest of time, but the quantum circuit describing a traversable wormhole, this is a photograph of the Google Sycamore quantum processor here. So now, this experiment has garnered a lot of criticism, and particularly, I guess I should say, especially in the way that it's been reported. Many, let's say, conventional physicists have gotten very upset at the suggestion that the researchers actually demonstrated passing information through a wormhole, a micro wormhole. And again, I think this has to do with the idea that, wormholes are a staple of science fiction. So, it's not seen as real science if you're talking about wormholes, even though it absolutely is. And it also, I think, gives the non-technical reader, the lay person, somewhat of a misinterpretation of what is being done, because they hear physicists create a wormhole, and you start thinking like, oh, so soon we're going to be able to travel through wormholes. But that's still quite a ways off from what was done here. Now, Leonard Susskind, who is kind of the foremost authority on this topic, he published a paper discussing the results of this experiment. And in it, he says, because 9 qubits can be easily simulated on a classical computer, the results of this experiment cannot teach us anything that cannot be learned from a classical computation, and will not teach us anything new about quantum gravity. I think, though, that he's missing an important fact of what was done in the experiment, and that was the operation of sparsification, where the researchers were able to simulate a large number of qubits with a small number. They used that neural network and the machine learning to preserve the gravitational dynamic signature of a large number of qubits in the SYK model. And they were able to simulate that. They were able to preserve that quantum gravity dynamic signature on a smaller number of qubits, so that they could actually use the 7 qubits, the 8 qubits that are available with the real quantum computer. So I think that he's kind of missing that point, even though I guess more technically he is correct that to really test this, we need a system that has many, many qubits. And, that is just going to require further technological development to build quantum computers that have more qubits. There's also problems with the ADS CFT holographic correspondence conjecture. One of those problems is that anti-de Sitter space is not de Sitter space. So anti-de Sitter space is a 5-dimensional manifold, and it's I believe a positively curved. It's a hyperbolic space-time geometry. And so one of the problems with using that is that in most cases, it appears that our actual universe has a more flat space-time geometry, and it's 4D, not 5D. Although it has been shown that at the larger scales, there is positive curvature to the universe. It does have a closed geometry, actually the geometry of a torus, double torus geometry. That's been experimentally and empirically demonstrated. There's a fundamental problem with doing gravity this way. String theories based on quantum gravity uses weakly coupled strings with the graviton a weakly coupled mode. But this theory is dual to strongly coupled gauge theory, where you can't calculate anything. So normally in string theory, they use weakly coupled strings to describe gravitons. weakly coupled modes. But the ADS-CFT uses strongly coupled gauge theory, which is not what is typically done. So ADS-CFT is telling you nothing about the usual picture of how gravity rises from string theory. What it supposedly tells you about are strongly coupled strings using weakly coupled gauge theory. And then the connection to gravity is something very different than what was originally advertised for string theory. So, this is basically showing that in terms of advancing string theory, it has done nothing, or I should say perhaps very little to advance string theory. But that's no problem for us because, there are many additional issues with string theory that show that it's not the best approach or even a good approach to unified physics. As quantum devices continue to improve, lower error rates and larger chips will allow deeper probes of gravitational phenomena. Unlike experiments such as LIGO that record data about gravity in the world around us, quantum computers provide a tool to explore theories of quantum gravity. We hope that quantum computers will help develop our understanding of future theories of quantum gravity beyond current models. Gravity is only one example of the unique ability of quantum computers to probe complex physical theories. Quantum processors can provide insight into time crystals, quantum chaos, and chemistry. The results of this wormhole on a chip, quantum gravity in the lab experiment has far-reaching consequences. From the fundamental physical interpretation of quantum mechanics, the understanding that particle interactions are occurring at the gravitational scale. That's an important one for the generalized holographic solution because Nassim Haramein has shown that the strong force is a gravitational interaction occurring at the atomic scale, subatomic scale. Consequences to a potential resolution of the constantly debated information loss paradox. Certainly, future experiments of this type will provide the empirical data and observations that will ultimately reveal the role of space-time geometry and particle physics and quantum mechanics. This work constitutes a step towards a larger program of probing gravitational physics using a quantum computer. However, it does not substitute for direct probes of quantum gravity in the same way as other planned future experiments that might probe quantum gravity effects in the future using quantum sensing. So for an example of this, you can see in my article, time dilation experiment with atomic clock opens possibility to measure relativistic effects in matter in quantum state. But it does offer a powerful testbed to exercise ideas of quantum gravity. But just to mention that there are other experiments that are being done that more directly, perhaps, test quantum gravity. And I've got a couple of articles on this, particularly using atomic clocks to measure time dilation effects in quantum entangled systems. And maybe just real quick, I should note that this work is also very much corresponds with the resolution of resolving the information loss paradox. And you can read more about that in my article on Eventful Horizon. And it's just, again, the role of wormholes, of multiply connected space-time geometry and black hole physics, where the information that is normally thought to be locked up inside that surface boundary, that event horizon, that information inside is actually outside. It's available outside as well via that multiply connected geometry. And, this is applied in Nassim's generalized holographic solution to output the massive black holes, micro black holes like fundamental particles as well. So all of those articles are available on the Resonance Science Foundation website. If you go to the science section, you can see all of our articles available there. So now I think we've got some time to take some questions. I can already see a hand up. So let me see if I can bring you up. Can be, I think all you need to do is just unmute and you can ask your question.
Right on, William. Man, you're knocking this thing out of the park. You're taking complicated topics and you're like spelling it out for kindergartners. I love it.
Thank you, thank you. Well, that was the chore with this one, was to try to explain this in a way that it's understandable.
Yeah. No, it's interesting because I had just seen a couple of days ago, I saw a YouTube video on the Quanta magazine, which actually took this and broke it all the way down into like a 15 or 20-minute video. I just put the link in the chat, but it was absolutely outstanding what they did. So hearing your presentation and then linking it in with kind of the Resonance Foundation model, I mean, I was really looking forward to this. It's like, oh my God, this has got to be a really interesting one. But all that said, my actual question, and I pretty much get a pretty good understanding of the physics of it, but I'm really curious, how has this finding, I mean, obviously validated a lot of everything that you guys are working on, but is this now going to kind of leverage your ability to start saying, let's really take a new look at this holographic universe model within the mainstream of science? And then the two other parts of that is, would it make sense? Does that give you an extra leg up to, let's say, talk to some of these people who've done the experiments and possibly have some further derivatives or expansions upon that experiment? And does it potentially expand the model of what a quantum computer can actually be, as opposed to being some multi-billion-dollar thing that's developed on a chip of silicon? Can we start expanding it more into a different framework, such as biology, without a yield?
Yeah. Oh, that's a excellent insight, because I'll kind of address that latter point first, because I think that that's absolutely the case. Is that when you understand better what is actually being done with quantum entanglement and with information processing of bits that are quantum entangled, or qubits. When you actually understand the underlying physical processes that are occurring, I think that it changes your perspective on what a quantum computer is. Because, the main ways that quantum computers, or the theoretical development behind them and the way that they're conceptualized, it's considering things like a superposition of states. So you're able to leverage a superposition of states where your normal bit that is 1 or 0 is in the superposition of both at the same time and everything in between. Now, the problem, though, with that idea is that when you go to measure your qubit that's in the superposition of every possible state, the output is always 1 or 0. You can't measure a superposition by its very definition. The superposition collapses into a definite position, 1 or 0. So really, what you're doing in kind of the best case scenario with a quantum computer is you're doing massive parallel processing. And so it's just that when your bits over here are processing information, they're so strongly correlated with a set of bits over here that the processing is occurring in parallel. So when these bits are switching states, it's affecting how these bits are switching states. Now, that's a really good description of how macromolecular systems work in the cell, in the biological system, how macromolecules work in the cell. They're extremely strongly correlated, i.e. entangled, quantum entangled. And so when you have processes occurring in the cell in a set of molecules over here, because they're so strongly correlated with the DNA in the genome over here, they're affecting each other non-locally, instantaneously. Indeed, I think that there's a potential to have breakthroughs in the conception of what a quantum computer is when you start to see it as a massively parallel processing device, and you can, take examples from biology and extrapolate that and actually, build quantum computers based on biological processes. A DNA computer could outperform a quantum computer almost any day of the week, especially in terms of massively parallel computations. You can use DNA to run computations.
I guess part of the interesting thing that I see is that the fact that you equate a quantum computer to massive parallelization means is that you have to have a massive number of sampling nodes to be able to define a very real correlation. So you might have, 100 million little sampling points, and you get a, a billion to 1% correlation. You said, hey, that's good because it's better than zero. But the thing that I see that is key to that is you have to have a substrate that has a certain level of fluidity and a certain level of memory. And so obviously plasma is a very good thing when you're looking at the solid state world, but then water might be the same thing in a biological world. Mm-hmm. So does that mean that we're going to start being able to explore a more water-based quantum computer, where, I don't know, maybe doesn't necessarily have to be proteins. I mean, you might be able to have some silicon or, carbon-based components to it, but using the ability for water to dynamically restructure itself and hold a pre-existing state so that the water itself can be part of the circuitry that then gets revealed through the quantum mechanics, or the quantum actually, the electronics, the sampling materials. Does that make sense?
Yeah, very much so. Because as you're, kind of contemplating what this future quantum computer might look like, what you're describing for me is beginning to describe the brain. You're painting a picture very similar to the architecture, cytoarchitectonics of the brain, where at the center of the brain are four hollow spaces filled with water, the ventricles filled with cerebrospinal fluid. So if you go to the core of the brain, what you'll find is water-filled cavities. They have their own pulsatile behavior, like a heartbeat, and they're pulsing that water through the brain. In some of the biophysics research we've done, there's these water-filled channels in the brain. They're not cushions for the brain. They're not just involved in helping with waste disposal of waste metabolites, and that kind of stuff. They're integrally involved in the memory and information and receptivity properties of the brain. And so, yeah, as quantum computer, as our idea of what a computer is advances, and particularly these quantum computers, we'll see that it's not really computational in the sense of flipping ones and zeros, your digital string of bits. A much better way of processing information is quasi-instantaneous transfer of information between multiply connected geometry of space-time frames. So that's what a traversable wormhole is. This latest experiment is starting to step into that realm where you're understanding, okay, your qubit, and when you do a quantum teleportation of your qubit systems, that's actually using a shortcut from one space-time frame to another via a traversable wormhole. In that way, space itself is the memory device, because if you want to access information about a previous state, that space-time reference frame is there. You can access it via a traversable wormhole. So you don't need to physically encode that information in some substrate. You can access it instantaneously, quasi-instantaneously through the traversable wormhole. Now, that's to me what massive parallel processing is. And that's to a great extent how our brains and even the information processes occurring in our cells, what they're doing. It's like the memory isn't stored in the neuronal network of the brain. It's being accessed directly, like a previous, a space-time coordinate in the past is being accessed almost directly via the micro wormhole network. Our quantum computers will actually start to go away from being what is conventionally thought of as computation. And you'll be doing this kind of quasi-instantaneous accession of information from any space-time reference frame. And as you're doing that with your computers, they're going to probably start to resemble more and more the biological system, which has had 4 billion plus years of optimization on how to construct a system that does that optimally.
Wow. Here's an interesting thought that kind of came, and then I see other hands up, is if you took a half a dozen tanks of algae and, you kind of created, that fourth phase of water with the cellulose and semi-permeable membranes and stuff, and then you put together some level of informational-based electromagnetic signals into those various tanks over a period of time to see if they would form a different structure, physical structure to represent the encoded information, and then to be able to see that if once those algae tanks got programmed, if then they could, in a sense, be trained in the same way the quantum computer would be.
That is an excellent example of where I think we can take this latest experiment and expand on it, and have other kind of examples, demonstrations, experiments showing the role of this entanglement network, this multiply connected geometry of space-time. And I think that one of the most promising applications as far as experiments to demonstrate this link between information and matter is with the biological system. I think that there are a number of really interesting experimental setups that can be designed to test this equivalence, this holographic equivalence between entanglement and micro wormholes using the biological system. And now, in the example you suggested, you're thinking that the algae, via this information transfer, could be trained to adopt a different kind of macro scale organization.
Yeah.
Because their kind of primary organization is the biofilm, right?
But it would be really interesting to see. I mean, normally people would think about doing it with neurons, but I would say if intelligence is part of a fundamental component of all living systems, and why not start with a very primitive living system, and to see how it can develop and encode that information, starting from very simple building blocks. And then at which point you have an incredibly fluid and very adaptable system. And once you get the mechanics down there, then you can take that to more higher and complex cellular structures. Yeah,
that's a really valid point in that, this intelligence and even what I would call sentience is present in even what is considered the most primitive of cells. It isn't just neurons and neuronal networks that have intelligence and sentient behavior. It's present in some of what we think of as the most simplest single-celled organism. And actually, I mean, if you look at the molecular complexity of a single-celled organism, it's absolutely mind-boggling how complex our simplest single-celled organism is. The kind of molecular dynamics that are occurring, the structural organization at the molecular scale of these single-celled simple organisms is absolutely phenomenal. Actually, just as a thought to that, you could use organisms like Nematostella. Animal-like organisms that don't have neurons but have somewhat complex, I don't know if I should use the word complex, but intricate body patterning, body arrangements. But following along the idea of using a more basal level organism, and then seeing if by coupling it with this information transfer, you can drive kind of like adaptations. That's similar to experiments that we've thought of to test things like the unified space memory network, the postulate within it. Yeah.
Let me yield to some other folks, because I think the essence is to demonstrate the intelligence is in the space and it has nothing to do with the structure. So the closer you can get to the basal level organisms, then it's going to be more obvious. So with that, thank you very much, and I yield and look forward to more. All right, take care.
Thank you, Ken. It's great to hear your thoughts on this. So let's see. Next up, I'll just go from top to bottom. I've got Venice Inventors. If you want to unmute, we can see your thoughts on this latest experiment and unified physics, unified science.
Hi, my name is Alexandra. I have less difficult questions than the one that it was just posed. But yes, so it seems that the entanglement is the most important part of the transfer of information and of the physical connection. It seems that entanglement is what enables what is really happening, process of the transfer of information, which is at the end the most important, because as you put, the picture you put before, where there is the black hole and the wormhole, there is transfer of information, and how much information is held into this surface area according to the volume and the or the event horizon. And it seems that the transfer of information is the key, and it's enabled by the entanglement. Is that correct? And what really means entanglement then?
Oh, well, first I want to make sure that I clarify, what you're thinking in regards to this, because, the way you're stating it is very general. It's like the transfer of information in general. And, I would just want to make sure that, we focused on this real specific case scenario of a transfer of information using quantum entanglement, the quantum teleportation. But I want to make sure that it's clear. There's myriad other ways to transfer information that don't involve quantum entanglement, quantum teleportation. I'm sure, though, I guess that you full well know that. It's just the way it was stated was very general, because I'm just thinking about resonant transmission of information. You can have two systems that are harmonically tuned to each other and have like a resonant transmission of information between them. It's essentially what a radio is, just to make clear that when we're discussing a quantum entanglement and the transfer of information, it's just this very specific case where that's a means of transferring information. But something that isn't kind of explicitly stated, but that I think is a very exciting implication about this experiment and this work, is the idea of developing technologies that are capable of non-local signaling, the transmission of information non-locally, which is perhaps kind of a very technical way of saying faster than the speed of light. Again, a quasi-instantaneous transmission of information. And I use the term quasi-instantaneous just, to refer to the actual physical mechanism by which this information is being transmitted, because it's not actually going faster than the speed of light. In many regards, that is impossible, because what you're doing is you can have a signal that its speed and its proper frame of reference could be at a snail's pace, could be very slow. But if it pops into a wormhole, even though its own frame of reference is going at the speed of a snail, it can pop out at a different space-time region nearly instantaneously. So, it's quasi-instantaneous transfer. But that's just because it's gone through this shortcut in the space-time geometry, this what you could almost think of as a hyperdimensional space. It's a very exciting possibility that this kind of experiment and the understanding that comes from it can be used to develop a system, develop a technology that can actually harness that multiply connected geometry of space-time to send non-local signals, seemingly faster than the speed of light. Now, you had asked, though, what is quantum entanglement in light of what we've just seen from this experiment, from the ADS-CFT holographic dual conjecture. What exactly is quantum entanglement? I think that this thankfully actually demystifies quantum entanglement to a large extent, because what you have is just two systems that are very strongly correlated. And that strong correlation is actually the information of that state is actually driving and stabilizing the underlying space-time geometry of those two systems. So because of that strong correlation, the information of that physical state is having, in the technical parlance of these experimenters, a gravitational back reaction that is actually stabilizing and strengthening the wormhole connection between those two systems. And so your quantum entanglement becomes very much just the directness and strength of that space-time channel, that space-time connection between the two systems. Because it's important to note that, especially if you look at our work on the Unified Space Memory Network, the micro wormhole network is constitutive. It's always there. So wormhole connections are always there. Everything, every fundamental particle is connected to every other fundamental particle through the micro wormhole network. And that's one reason why a lot of the articles that have discussed this laser experiment, like that in Quantum Magazine, are somewhat frustrating for us at the Resonance Science Foundation, because it's oftentimes described as this wormhole was created, it was generated. And you're not technically creating or generating a wormhole. The wormholes are always there. The wormhole connections are always there. Because I actually, to bend space-time into a wormhole, it takes almost an infinite amount of negative energy. So it's very difficult to create a wormhole out of de novo synthesis from scratch. Utilization of wormholes, and especially the technological utilization of wormholes, will be utilizing the pre-existing wormhole network. So really what you're doing when you're getting maximal entanglement between two systems, they were already entangled. It's just that the entanglement network, the entanglement nexus of space memory, might have been a very circuitous path through that entanglement network. Mm-hmm. So that, that correlation between the two is not obvious, because first, if this particle has an interaction, it interacts with this particle, this particle, this particle, this particle, before it gets over here. And so you don't see the direct connection. You don't see the correlation, the entanglement between the two. And what you do with quantum experiments with a qubit state, a quantum computer, is that you minimize the number of, let's call it, extraneous connections of your system. And you do that by lowering the temperature, putting it in a vacuum, like a real vacuum, so evacuating all the air out of a chamber and putting your little particle in there. And by doing that, and then, having a microwave pulse between two systems in such a state you can entangle them. And now your entanglement network isn't so circuitous. It's much more direct between the two. So instead of weak correlation, you have strong correlation, and that's quantum entanglement. I don't know if that helps.
Yes, it does, definitely.
Okay.
Thank you so much. Especially the part that you say is technological utilization, as opposed to we could make the wormhole, which you already clarified to me that it is impossible.
Well, I don't like to use the word impossible because probably I'll get proved wrong. But let's just say it's unnecessary.
Unnecessary.
To create a wormhole from scratch. I mean, you could do it. I mean, especially a micro wormhole, because if it's like a Planck scale micro wormhole, all you need is the Planck energy. 10 to the -5 grams per meter cubed. If you can get that much energy into a Planck distance, you'll make a black hole. You'll make a wormhole. But let's just say more so that it's unnecessary, because why would you do that when there is a constitutive network of Planck scale wormholes already? Actually, so for like technological application, probably what you would be doing is bundling all those microscopic wormholes up together. By bundling more and more of them together, you could create a macro scale wormhole, traversable wormhole that maybe you could send a person through, a ship through, or maybe more initially you could send messages through, because if you're doing like interstellar travel, you're going to need, and you want to communicate with your interstellar travelers, from Earth to 8, 10, 20 light years away. You're not going to communicate with them using radio waves. Because for one, you need a really powerful radio beam directly targeted at them. And if they're 20 light years away, it'll take 40 years to send a message and get a reply. You need non-local signaling for interstellar communication. Yeah, but so it's really interesting though, because I'd mentioned Leonard Susskind. Some of his most recent work on actually advancing the ADS-CFT correspondence conjecture is, so one of the problems with it is that it's using anti-de Sitter 5-dimensional space-time. Space, I should say. So he's found a way to actually describe it with de Sitter space, which is more akin to the Minkowski space-time that describes our universe. And one of the ways that he's done that is by describing the bundling of micro wormholes into a single wormhole. This is already being applied theoretically to solve for some of the problems in the holographic principle and the holographic duality. So it's already being applied theoretically. The next step possibly is applying that technologically.
So when you have the conglomeration of these wormholes, that will be a parallel transfer of information.
I'm sorry, what do you mean by that? Maybe if you say that again.
Okay, so when you will have theoretically the accumulation of wormholes all together, working as a system, then the transfer of information could be like as parallel, because it will be all of them at the same time.
Well, I mean, yes, but the idea is that as you bring all of those to, let's say, micro wormholes together, and you start to bundle them together, from your vantage point, from your perspective, they're very much like a single channel. So technically, yeah, it would be like transferring in parallel. But I think for all intensive purposes, it would appear to you as a single large macroscopic wormhole. So it's just that the idea of the parallelism for me is kind of involving two systems, two or more systems, transferring at the same time. But I guess technically, since it is a composite structure of many micro wormholes bundled together, it is a parallel transfer. Yeah. I'm not sure though. I mean, as you bundle them, they might actually merge, so that they do become just like a single structure. I'm not sure what the mathematics say about that. What theory predicts for that. I think that there's been computations that show it going either way.
Thank you so much for taking my very elementary questions.
No, those are great questions. Yeah, very much appreciate you sharing your thoughts with us, and I hope to definitely get more of your questions in later sessions. They're excellent.
Thank you.
Thank you. So next up on my list here, I have Cosmic Simon. If you could
yes,
unmute. Okay.
Hello, William. Oh yeah, actually we just spoke a couple of weeks ago on my question about cells having photons in communication.
Oh yeah, okay, yeah. For our the faculty Q&A session in February. Yeah.
Yes. Thank you so much. Doing a mess. So building on the last two questions, I'm trying to simplify the best I can. So we talked about transfer of information in the quantum scale, and basically you mentioned 5D in the light of what I think holographic correspondence versus 4D. So I'm coming from the interpretation of our universe as an architect in a much more visionary way. So 4D and 3D, as you described it over the past hour and a half with other things, is very clear. I don't quite get the 5D, and I'm wondering if that has to do with holographic, because there's a lot of 5D mentioned in spiritual, and I want to hear it more in terms of how maybe others got it, but I missed qualifying what that was. So the 4D was like we live in a 4D space, and then the new physics is really qualifying that in terms of a holographic universe, but not like we see in the typical mainstream, like, from a 2D surface, we're holographically 3D. What is 5D? When you mentioned that, I didn't quite get that. Is that non-local? And then does that have to do with, I wrote it down, deserter space? Is that somebody's name, and does that have to do with that?
Yeah. No, so this
That's
is
what I'm asking. Yeah.
This is a great point of clarification, especially when we're taking these highly technical terms from kind of advanced physics. This is the bleeding edge of physics. Unified physics, holographic theory. And applying it in a non-technical setting, there definitely is some very real disconnect there that absolutely requires some clarification, because in our kind of non-technical parlance, when we use the term dimension, we can mean almost any a couple of different things. I mean, in popular kind of stories, there's the idea of parallel dimensions, and actually oftentimes what that term is meant to convey is parallel universes.
Right.
Then within the spiritual terminology, there are higher dimensions, and oftentimes this is actually more trying to convey different like density, energy densities, so actually kind of more akin to like the electromagnetic spectrum, where we are aware of a tiny minute fraction of the entire range of electromagnetic energies. So even though we're only tuned to like a very small frequency range, there are much higher frequencies, much lower frequencies that we don't directly observe, but nevertheless are there. And I think that's oftentimes how dimensionality is used in spiritual terms. Now, neither of those is how is what is being referred to in the technical parlance of holographic physics, the holographic principle, because here it's using the very conventional definition of dimension as a spatial property.
Okay.
So dimensionality is measured by things like rulers, and I mention it that way because that's the beginning of Einstein's special theory of relativity, is a discussion of clocks and rulers. So how we measure the physical dimensions of our universe. And actually, it was his considerations of clocks and rulers that led him to the general theory of relativity, and how clocks and rulers can actually change size and frequency depending on whether you're accelerating or in a gravitational field. But so, in the very technical application of the term, dimension is referring to physical spatial dimensionality. And it's much more appropriate to view it in terms of mathematics, in terms of geometry. We can draw a straight line that is one-dimensional. So, an imaginary being on that straight line in that 1D space can move left or can move right, but that's it. But then we could add another dimension to that, and then a third dimension, and now your straight line has become a cube, or let's say a sphere. And so now your hypothetical being in that 3D space has many more degrees of freedom in its movement. It can move left, right, forward, back, up, down. Well, mathematically and geometrically, there's absolutely nothing stopping you from adding another dimension. And so you could have 4 spatial dimensions, and now you've got a hypercube. And so now, your hypothetical being in that 4D space has an additional degree of freedom in its movement in spatial dimension. It can move forward, back, left, right, up, down, but also at a 90-degree angle to all of those ranges of motion. Now, again, that's kind of an approximation of what that motion would feel like or look like, because, even, a 90-degree angle to our upright left down, that's still a 3D notion. But that's our closest approximation to what we can get. And, I think it's interesting because, I think it's possible that there are, in fact, 4-dimensional spaces possible even in our physical universe. So real physical 4-dimensional spaces. And so, if you had an object or a being that was capable of moving in 4 physical dimensions of space, to us, it would have some pretty interesting properties. Like it could instantly seemingly pop out of existence in one location and appear in another. But really all that it was doing was moving in one of those extra spatial dimensions. And so that's kind of like akin to if you have a being restricted on a one-dimensional surface, but you can move in 2 dimensions, you could jump into that extra dimension. The being wouldn't be able to see you, and you could pop in at any location by traversing in that other dimension. So that's the idea of dimensionality in this more technical terminology. And then, so we got anti-de Sitter space. And indeed, that's based on the work of an astrophysicist, mathematician, de Sitter. Actually, I don't know if I know his full name offhand. Let's say Dr. de Sitter, though. And so, de Sitter space is a very close approximation to describing the real physical dimensionality that we observe in our universe. 3 physical spatial dimensions and a temporal dimension, a dimension of time. Well, there's the curvature for that is flat or even slightly negatively curved, I believe. But then so you can reverse all of that and you get an anti-de Sitter space. And when that's done, you end up with a 5-dimensional space. And, again, this is how it's described in the mathematics. Geometrically, as I was saying, you can add as many dimensions onto a mathematical equation as you like. And that's one of the reasons why string theorists end up with 11 dimensions. And actually, we were all having a good laugh at one that had 26 plus 1 dimensions, on it.
Yes, yeah. They keep going on and on and on.
And one of the problems with that is, how physical are extra dimensions?
And that was like the basis. Sorry to interrupt. Yeah, like is for you, like you and Nassim, and is 5D a real, not just mathematical interest? Is it a reality like 4D is?
No. So
okay.
While we might kind of entertain thoughts about that, like I like to think about the real possibility of an actual physical 4th spatial dimension. I kind of think that there's a possibility that could be real. But in terms of the physics, it is all much more elegant, and the solutions are much better when you have 3 spatial dimensions and 1 temporal dimension.
Okay.
And so actually, in our work, we are applying a holographic principle to that, and that, we have a 4D space-time, and that is showing how time has properties very similar to a spatial dimension.
Yeah.
And it's that, in a spatial dimension, if you move from point A to point B, point A doesn't disappear because you're at point B. But, in our conceptions of time, if you go from time point A to time point B, time point A has disappeared. It no longer exists. One of the things that Einstein and general relativity did was say, no, time is much more like a spatial dimension. And just because you're at point B doesn't mean point A is gone. It's existing concurrently, simultaneously. And so actually, all frames of reference are occurring instantaneously, simultaneously. So, what we think of as the past isn't gone just because we're at point B and it was point A. And what we think of as the future isn't non-existent just because it's point C and we're at point B. Now, you take that a step further, though, and start to apply the unified physics principle and the holographic principle, you can get a further characterization of what is time. Well, actually, time is a holographic projection in many sense, and therefore illusionary, of information encoded in 3D space in Planck voxels. And that's what we call space memory. And so it's very much the entanglement, quantum entanglement, the connectivity circuits of space that lead to the emergent experience of a dimension of time.
Mm. Okay. Yeah. That is, I'll listen to it again.
Okay.
much more, but it just grounded it a lot more for me.
Okay, excellent.
For others. Thank you.
Yeah. Well, and I think you were on the right line of thinking there, just that, that the anti-de Sitter space is problematic, because it doesn't really have, it doesn't, to our knowledge, to our understanding, it doesn't actually correlate with anything real in our physical universe.
Yeah, I just wanted to ground it more there because it's easy to get into these nuances of space and scale. And the other thing I really acknowledge the Science Foundation is scales. And it could really relate to how the new physics relates to the scalar dimensions. And I think without asking specifically, you just answered the distinction of what that is, a fifth dimension versus scalar dimension.
Mm-hmm.
I don't know if I'm answering this right, but like everything, like some other people, I have to listen to this about 5 times afterwards. Thank you, William.
Oh, thank you for the question. Yeah, and at risk of confusing the topic, I would like to also mention, though, models of early models of unification physics that were unifying Minkowski space-time with Maxwell's electromagnetism, and these were called a Kaluza-Klein model.
Oh yeah,
and it's very interesting because in their work they were able to show mathematically that they could unify physics, and this was early. I don't know the exact dates, but I mean 1920s, somewhere around there. And they were able to show the equivalence of the electromagnetic force with gravitational interaction. And one of the ways that they did that is they were unified in a 5-dimensional manifold. So when they used 5 dimensions, they were able to have a single equation that would describe electromagnetism and gravity. Kind of interesting, So it's one of the reasons I don't outright discount the possibility of spatial dimensions beyond what we're aware of. But that was back in the 1920s, and so why didn't physics get unified from that theory? Well, there are other problems with it, and like the work we're showing, the work especially that Nassim has done is showing that there's much more simpler ways to solve for this than including fifth dimension that we don't even know if there is a 5th spatial dimension or a 4th spatial dimension, for that matter.
Yeah, thanks for bringing that up. That really helps out. Because I also know that I think you mentioned in the faculty session, but also Nassim has mentioned as well. I mean, if Einstein said in general, if it's not simply explained, then it's probably not accurate in terms of physics, right? And
that's a lot of what we have going on right now is that you have really smart people working on this idea of unified physics, and they kind of like to work with things that are very complex and things that only them and their friends can understand. And so, but one of the problems with that is that the universe actually doesn't utilize such complexity, especially at fundamental levels, at fundamental physics. Solutions are oftentimes very simplistic and elegant. E equals mc squared kind of elegance, yeah.
Yeah. Well, thank you so much. Thank you for all the work that all of you are doing, and I appreciate the time.
Oh, thank you. Yeah, thank you so much for sharing your thoughts with us. So we're a little bit over time, but I think I can manage to take one more. Maybe might have to keep it kind of concise, kind of quick. Next up, I have Beth Hazard. If you unmute, we can hear your thoughts on this discussion.
Hi. Okay, let's see. This is exciting. This is a really great talk, but I will try to stay concise, even though I have kind of a crazy question. So I'm an acupuncturist, and I do distal acupuncture, meaning it's working, to me, it works through this entanglement nexus within the biological system. So you have a local area of, let's just say pain, for instance, right? And then you choose a distal location that, what's fascinating to me is that it has what seems to be an instantaneous response. And it's not like, it could be a shoulder on one side of the body and an ankle on the other. So the whole idea that it's traveling through the nervous system, making some sort of change at that level doesn't really make a whole lot of sense in terms of how fast, and actually the two locations, although everything's connected through the nervous system, it's not like this really easy relationship, if that makes sense. So what's interesting is we use a few different systems to choose the distal point. And so you would use self-similar locations. So if you had like a really obvious one would be like a shoulder and a hip, right? So they're kind of an opposite shoulder to hip, these analogous larger joints in the body, right? You could also theoretically, if you don't have access to the hip as your distal point, you can flip the whole image and put it in the ankle, and it works. But part of how we choose would be based on relationships between meridians, right? Between the points. One of those relationships is what we call a clock opposite. So you're looking at the Chinese biological clock, and you're basically moving through the clock to choose the meridian at the distal location in a self-similar part of the body, right? So when you started talking about, well, for one, it makes me think about, in some ways I've used this and I'm like, what is that though? Why is that working? Why is that clock opposite the thing? And it's not the only one, but it's one. And it works a lot of the time. And it's kind of like, you start to think about how we're moving through space and embedding on the fabric of existence and leaving our little bits of information through that space memory network, right? And so is it the local area of complaint having an entanglement nexus with that actual location of the original, let's say, injury, and then you're somehow working through the clock there to get to this other meridian? I'm just like, how does it work? Is time dilation part of it?
That's a very interesting idea, because just kind of hearing about it for the first time here, one of the things that I could imagine why it is an effective methodology is that, so that let's say injury imprint in space memory, while it might have while it might correspond with, like, say, the shoulder, as you're moving through space-time, you're spiraling through.
Yes.
So it might be that by the time you're having it done,
yes.
The actual part of your body that best corresponds to that space-time location is the hip, because you've kind of like rotated you know, it's a possibility.
It is a possibility.
Yeah,
I like that because I think of it that way. I'm always thinking you're spiraling, you know, as we're moving through the, that is good stuff.
But,
okay.
You know, the meridians though, you know,
Yes.
absolutely. In the kind of investigations we've done into the biophysics of, let's say, the connective tissue network,
Yes.
very much you have strong correlations between distal regions of the body via the meridian network. And, you know, there's actual physiological correlates with the acupuncture meridian network.
Yeah.
You know, those physiological correlates are part of what's generally called the connective tissue network. But one of the things that you can see with the connective tissue network, if you're talking about like collagen fibrils that are connecting distal regions, you know, they're hypersaturated with liquid crystalline water.
Yes.
You know, and so this is a property of many extracellular tissues, extracellular connective tissues. They hold a lot of water. They're very hydrophilic. One of the things, though, is that liquid crystalline water, like what exists along the meridian channels of the body, you know, it behaves very differently than kind of normal bulk water, unstructured water. And it actually has observable and documented quantum mechanical properties. One of those is that it can have like superconducting signals where it's superconducting, or it's called ballistic conduction of protons, which are involving quantum tunneling, which is very much equivalent to quantum entanglement, where basically bioelectrical signals, bioenergetic signals can be transmitted from one region of the body to another nearly instantaneously via tunneling of these protons along the networks of liquid crystalline water.
Well, I will say, when I do this type of acupuncture and I'll palpate and find like an affected area, something that's tight, let's just say that, in the musculature, in the fascia, right? I go and I needle the distal area and I come back, and it could even be like something right over a vertebrae, for instance, and you will feel it in that liquid crystal structure. I'm like, I don't know how to describe what I'm feeling, but it's like it goes, and I feel this little
it's
shift.
something like solid that's been in there.
Yeah, it's like liquid. It becomes liquid, and I always say, "Oh, now it's juicy." It was like somehow like kind of like all, you know, like solid or like crystallized, but more in like a solid way, and then it becomes like more fluid and moving. But I'll feel like in tissue, it's sometimes it's obvious, like a muscle releases, but sometimes it's so subtle, and it is just when you're saying that, I'm like, that's where I'm feeling it. When I go back to check. And it just, I'm like, oh, it happened. It's changing. So anyway,
that could have been a real like physical obstruction to that flow of bioenergy. Yeah.
Yes.
I'm curious. So you do the distal acupuncture, but is this because you found that it's more effective than like
the local
than doing it directly at the
well,
local spot?
There's a couple of things. One is I do shiatsu as well, which is body work. So it leaves my local area available for body work. If I have needles in the ankle, I can still work on the shoulder or whatever, right? That was part of my motivation. I also feel that it is illustrating, to me, it's like you can mechanically change something by just putting a needle into a local area, but there's something quite elegant about the system itself and how it's really proving a couple of things. One, I think the quantum field entanglement theory, it's really proving that to me time and again, and I get excited every single time. But then it's also showing how this the meridian system really works and the intricacy of it. So, because that's just one system would be through the clock, another would be through what we call these 6 stages, which I think are like the 6 stages of thermodynamics. And that's a whole other question, because those relationships also work in a local distal acupuncture situation. And I'm like, when you look at that thermodynamic toroid thing and how it's all moving through, it doesn't that look like the yin yang 3-dimensional yin yang structure, like it's moving through yin and yang.
Well,
anyway, and then that's happening at all scales of the universe, right? That's like happening in our seasons, in weather patterns. It's happening, through all scales of cosmology. You've got it at this meso level doing it here, and then you've got it reflected in these bigger cycles, both bigger and smaller cycles.
And I can imagine that, working with the body more at like the holographic imprint of the body, that, you can not only affect that distal region that is your target, but it'll also have parallel effects with many other connected systems that perhaps weren't identified or unintentional benefits of having worked with the holographic information network of the body.
Absolutely. Well, and it'll be interesting because you'll have the distal meridian then is relevant, that comes up around what's happening locally, could be relevant to another set of symptoms potentially, or even more existentially around like what's going on in the person's life or whatever. It should tick more than one box, really, if we're getting it right. Yeah.
Well, it's an excellent example of, the role of quantum entanglement in the body, because, we can theorize about it and look at, some of the mathematics and the biophysics of it. You're working with it. You're utilizing it, So it's like, you're kind of one step ahead of the theorists. Yeah.
Every day. And every time I listen to you talk, I'm like, this is it. So I appreciate it so much. I appreciate what you're doing. And I take notes and listen and try to make sense out of all of it. And I'm going to read your articles on the time dilation, because I feel like there's going to be some little tidbits in there that might open my mind up a little more to how that's working. But I really like what you said about the spiral. That makes so much sense. Yeah.
There's also a really good article in Quantum Magazine on. I'm wondering if I still have it up on my computer, but experiments that have been done that show how you can change something in the past by affecting the present. And I'm sure that in one of those articles I mentioned, that is cited. But
there's a whole other system of meridians that are deeper to the 12 regular meridians called the 8 extraordinary vessels that are ancestral. And there's a whole system within that's time-based acupuncture or chronoacupuncture.
Oh, interesting.
And you can put a time in and find out which one of those ancestral vessels is coming up. So that might suggest not only are we doing our trajectory through space, but also tapping into potential points in our ancestry that are coming, we can access through sort of a time portal by opening up those points. And I've been using the art crystals for that. It's been really interesting. Yeah.
Oh, fantastic. Yeah.
It's cool stuff.
Excellent.
Yeah.
So, I didn't see the article, but if you look on Quantum Magazine, for time entanglement. Okay, I'll look it up. It'll probably be a pretty good reference for the work you're doing. Thank you so much, Beth, and
thank you.
Thank you, everyone, for joining us. And I'll definitely be looking forward to our next Unified Science review. Hopefully, we'll be doing these periodically. The next one that I'm hoping to do, or at least a subsequent one, is going to be following on this idea of quantum teleportation via traversable wormhole. And we're going to look at a recent experiment where they were able to transmit energy via a quantum teleportation-like protocol, quantum energy teleportation. So we'll be looking at that, and it's kind of a first time this has ever been done because, physicists have been able to teleport non-physical properties like information, an information state, the qubit state of A to a set of qubits at B. Teleport the information state from A to B. But physical property like energy, the energy of the system, that has never been quantum teleported before. And, it's kind of a different animal, if you will, because, if you can teleport that energy, you could use that energy to do work, power a device, among other things. So it's a very interesting thing. So I'm hoping that if not the next, definitely in a subsequent review of latest discoveries in unified science, we're going to be looking at quantum energy teleportation, and we can reference it back to what we discussed today to see how this might be described optimally via the space-time geometry of wormholes. So I hope you can join us for that, and certainly looking forward to it. Take care all, and may the vacuum be with you.